Okay, we are starting a new lecture, and that is a lecture, what I'm labeling it as Lecture 6. The PDF is on Canvas. It's a lecture on solving systems of linear equations. And this is sort of some of the core of numerical methods is actually solving either one equation, which was root equations that we just said, that we just covered. And this is now systems of equations. Now, most often, we're actually going to do linear equations, which is a simpler form of an equation compared to anything complicated that it could be nonlinear. And it's core because even when they're nonlinear, it's often the set of equations is linearized or approximated with linear equations. So ultimately, you end up solving systems of linear equations. Basically, most of you have either taken differential equations or are in differential equations right now, right? So when solving differential equations numerically, what it comes down to is no matter which method you use to discretize the equation, you end up solving a linear system. So is that important? So essentially, solving linear systems is one of the most important topics in numerical methods. Okay, so you've likely seen something like this, probably even high school. But if not in high school, then relatively recently here at UT. This is a system of two equations in two unknowns. How I call my unknowns is really irrelevant. But when we have many unknowns, we prefer to number them. So instead of X, Y, Z, or W, or whatever letters of alphabet, which I'm limited to on the order of 30 characters, okay? We typically want to number them, so use X1, X2, X3, and so forth, because that can keep going to however many I need. And in Python, of course, we're going to start with X0. Okay? So how would you attempt to solve this? Elimination. So there's a number of different ways, and you kind of start solving it on by hand. Here, there's plus y minus y that kind of calls for elimination. So if I add these two up, I'm going to get that 2x is equal to 6. So x is 3, and then I can plug that in whichever other equation to find y. So 2x2 systems are relatively easy, and you can even, if you're just kind of like tapping along and using your common sense, you can find a solution. Okay? The problem, and this class is a numerical methods, the problem is larger systems. Okay? So common sense is one thing, but you actually have to come up with a system or algorithm that computer can clearly apply in all possibilities. Right? And that's where we want to end up this semester. So this, again, you have seen it somewhere, and you can probably solve it. I found this on the interwebs. I thought that was cute. Life is one half happy and one half sad. Anyway, this is a linear system too. Everybody get it? Only like 5 people are smiling. Did you get this? All right. Little cheesy, but it's a linear system nevertheless. All right. This is more serious stuff. Okay, so this is the numbered stuff where I have many equations and many unknowns. Then I have to order them. Okay, so our most generalized system sounds like I have some set of coefficients which I'm labeling as A. So I have A11 multiplying x1 plus A12 multiplying x2 and so forth up to A1n multiplying xn is equal to B1. That's my equation 1. And then I proceed in a similar manner. So I have A21 multiplying x1, and I keep going all the way to A2n multiplying xn is equal to B2. And I can proceed like that. So this here, I have n equations. And actually, if I pay a little attention, this is inner product of a vector that has a11, a12 all the way to a1n, and vector x1, x2 all the way to xn. This is an inner product of a slightly different vector of coefficients, and again a vector x1, x2 all the way to xn. So if I organize all of the coefficients A into rows of a matrix, and my x1, x2 all the way to xn as a column vector, okay, then this first line up there is what I would get if I was multiplying matrix A with vector x, okay? Row dot product or inner product with the column, right? So essentially, I can organize this as a matrix A, x is equal to B. Okay? So let's see whether we can tease out, in this case, if my vector is xy, okay, x, then what is the matrix of coefficients that multiplies that is equivalent to this linear system? What are the coefficients in first row?
1, 1, 1.
So I write them as a first row of a matrix, right? So I have 1, 1, 1 minus 1 multiplying vector xy, and that is on the right-hand side equal to vector with 4 and 2. Does everybody see that? Okay. So I can do that with as many equations as I want. What's very important about that is now I have a system, that's what linear algebra is for, okay? For handling any size of a system, okay? And I can basically then proceed and create algorithms that just, you give me A and B, and I'm going to give you a solution, okay? So basically, this generalization is always very, very important in ultimately creating algorithms that work for any size of the system. Because again, 2 by 2, 3 by 3, you're going to be able to do by hand, not a problem. Question is, what do you do with a larger system? And most likely, larger than 4 by 4, you're not going to do by hand. That's just what is. All right. So I would like you to kind of, and we will do a couple of exercises, but basically a lot of different equations that can be thrown at you, but you need to kind of, in some shape or form, you need to put them in this form in order to use algorithms. Okay? So this AX is equal to B, so anything that I don't know is on the left-hand side, everything that I know is on the right-hand side, is an important form of writing down equations. All right, so just to give you some motivation, when I say that all of the discretization of the differential equations ultimately ends up solving a linear system. So you don't necessarily see it, but it's underneath, and we're going to go through some exercises that do that, though not in a full extent because this is an introductory class. So here's an example of a physical application that is important. What you're seeing is half of the well bore. That's where actually white empty stuff is. And the color is the stress field in the horizontal plane. So this is kind of cutting through a well bore. This is my well bore. I'm cutting through and I'm looking at a half because the rest is symmetric. What happens in subsurface, and you're going to get to that in geomechanics and drilling, is that you often, not often, most of the time, it's not even often, it's pretty much all the time, you have uneven stresses acting in different directions. And stress field, which you might or might not know now from statics, you can describe by 3 major stresses in 3 orthogonal directions, right? And those in horizontal, so vertical is most often one of those directions, simply because that's how you stack things up and weight in the subsurface. And then in horizontal direction, I have 2 other stresses. Here they're labeled sigma lowercase h and sigma uppercase h. Okay? So one of them is squeezing, this uppercase h is squeezing a little more than the other. Okay? That creates problems. Because of that, I might actually, along this larger stress direction, I might alleviate stress by fracturing. Okay, and that's essentially hydraulic fracturing. It often happens when my pressure in the fluid that is in the wellbore overcomes the smaller of the stresses. This smaller one right here. Okay, and the moment that pressure, fluid pressure, kind of acts on all directions, the moment I overcome the smaller stress, I crack. Okay, so monitoring the stresses, and especially then what is the stress field at this fracture tip, it determines how the fracture will propagate further into the reservoir. So of course, in petroleum engineering, we're interested in solving for this and figuring out how does it happen. At the same time, this is not necessarily shown here in any dramatic color, but there is also stress that piles up right here. And that stress here can crumble the rock. Okay? And I could have what's called wellbore breakouts. And wellbore breakouts are all fine until they're small. But if they go and start kind of dominating that entire top portion, I will have the well collapse. Okay? And it all kinds of depends on what is the wellbore pressure, which is the only one that I'm actually in control of. Okay? So we have to learn how to control and sort of optimize. Sometimes, most of the time during the drilling, I don't want to open a fracture. But then later during stimulation, I want to hydraulically fracture the well to stimulate. Okay? If I, during drilling, open a fracture, that fracture will steal my drilling fluids. Will I be able to replenish as fast as it can steal? That balance determines whether I'm going to be stable or not during drilling. Okay? But later on, once I actually complete the well, I might want to hydraulically fracture. Then I'm going to, by design, go above the fracture pressure to actually create the fracture to stimulate the well. Okay? But that's a controlled situation. Right? During drilling, it's not controlled. So sometimes those are both objectives that we want to achieve at different times. Either way, we want to figure out where that happens. Now, this is a long story that you're going to go into way more detail in geomechanics and drilling. But I'm just saying that in the simulation, if we want to actually predict what the stress field looks like so I can control the process better, I actually have to solve the system of linear equations underneath. So that's why when you kind of lose track in this lecture, like, why am I doing all of these nitty-gritty and solving the linear systems? That will be probably the smaller test systems, right? That don't look like they're solving anything important. Oh, yes, it's important. Okay? It's very, very important because, again, most of the differential equations, they require solving linear system over and over again. Okay? Now, so just to sort out some notation before we move on, normally to actually have a unique solution, I have to have a system of n equations and n unknowns. So I should have a square matrix describing my system. And that matrix should actually have an inverse. And what that means is that no two rows should be linearly dependent. Okay? And no linear combination of two rows should end up being able to represent another row. Okay? Because that means that one of these equations that I posed is actually not relevant. It's not relevant information. I already have it somewhere else. If I have more equations than unknowns, that's an overdetermined system. That can be a problem, of course. Then in that case, one of them better be a linear combination of the others, because otherwise I won't be able to solve. And when I have less equations than I have unknowns, that's quite a possibility. Then I have underdetermined systems, so I can just put some limits and solve the problem in parametric form. Okay, so for instance, one example, a simple one. If I have x plus 1 is 1 and 2x plus 2y is 2, do I actually have a properly determined system? Do I have a unique solution? So the second one is twice the first. So that's a simple equation. So it doesn't bring any new constraint, any new information. Therefore, I'll really only have one equation. Is that a problem always? No, I just have more options here. All x and y's that are on the line x plus y is 1, also known as a line y is equal to 1 minus x, all of them solve my problem, which is from the engineering standpoint not a bad idea to have more. Okay? So let's say that I'm solving traffic problems, right? And I design my traffic light around some streets here around this building, right? So that only the flow of cars that has precisely the number of the cars that I need on Speedway versus Dean Keaton versus some other, right? Let's assume that's the only solution to the traffic flowing through. That's a bad idea, right? So I actually want to have an underdetermined system. So as long as my flux of, number of cars on Speedway is between 0 and 50, right? I can figure it out. The same for all the surrounding streets. Do you see that? So those are these underdetermined systems. They better be underdetermined, otherwise I'm in trouble, right? It's like I cannot drive around this building unless there's precisely 3 cars on Speedway and 4 on Dean Keaton. That would be a bad idea. So underdetermined is not always a problem. All right. And there are some special matrices. This is just for your notes. If I have a diagonal, we already saw diagonal matrix. Matrix inverse is so-called a matrix A inverse, such that when I multiply A, I get an identity matrix. And technically, if I have an inverse, okay, then I can easily solve the problem. I multiply with an inverse, and then my identity times x, which is always x, is equal to A inverse B. So problem solved. Except that I rarely have an inverse. And actually, finding an inverse is equivalent to solving a system of linear equations. Okay? So if I have an inverse, great, I can always find a solution. But the problem is that finding an inverse is equivalent to solving a system. So in that sense, and we're going to get to that, we're going to do that by hand. And this lecture will be part by hand, so we will review in a slightly different way what you're doing in differential equations. And then we're going to just program it, but we're going to review it so you can program it, right? Just in case 2 classes are out of sync. And then the symmetric matrices are those that are symmetric along a diagonal. Right. I'm going to not focus on that. Let's go on to your worksheet. So does those of you who walked in slightly late, there's some extra worksheets. Behind you. Yeah. Extras here. Everybody has one. Back hand if you don't. There's some sent to the back. Excellent. So I want you just to kind of review what you possibly already know about solving small systems of equations by hand. And again, I want to just review so you can actually program later. So if I have this very small system, and this one is slightly different from let me open the worksheet. For some reason I decided to change. All right. So if I have 2 by 2, pick a method, however it is that you'd like. And if some of you were already sketching things while I was talking, we'll keep going on the sheet. So the second part, basically, take this as an x1. direction and this is an x2 direction. You can sketch both of these equations as lines. So try to find intersection of those lines. And remember that in order to draw a line, you need 2 points on that line. So plug in some values that Has everybody managed to work through 1 and 2? Yes? I just want to comment them before we move on. So essentially, however you pick 2 points on each of those lines, you choose an x1 and figure out what x2 is, find 2 points, draw a line, draw the second line, then your solution is intersection of these 2 lines. Okay? Do we see geometrically how this could go wrong? Do I always have a solution? No? So the lines could be parallel. Then they never intersect, right? And that's this case where I don't have a solution. Okay? The lines could be basically fall on top of each other. That's when I just multiply one of the equations by some number. And then that's essentially the same equation, so the entire line is a solution. Okay? And then they could intersect at a unique point. What could happen if I have more? If I have actually 3 unknowns, then I need 3 equations. What is one equation like x1 plus x2 plus x3 is equal to 7? What is that geometrically in 3 dimensions?
3D line, a plane.
3D line. A plane, also known as a plane. Okay. 3D line? No, 3D line. I need 3D version of a line is a plane. The lines do exist in 3D as well. Okay. So I have one plane. Okay. So there's of course infinite number of points in one plane. And when you actually have x1 plus x2 plus x3 is equal to whatever number, you need to define a plane in 3D. You need a point in that plane, okay, or a point in space. And then you also need to uniquely determine sort of a normal to that plane. Okay. And that normal, when I write down x1 plus x2 plus x3, normal is 1, 1, 1. These coefficients next to x1, x2, x3, or x, y, z, however you name those unknowns, that's actually the normal. Okay. Just an FYI. So anyway, so if I have this plane, and then I have another plane, I could have a line at the intersection of those two planes, right? And I need the third plane. Can you borrow me your paper and strike a third plane somewhere in space that intersects these two? Make it simple to yourself. Okay, there. So do we see a point at the intersection of three planes? Okay. So that point would be then solution if I have three planes that are in general directions. If two of them are parallel, I will have no solution, right? Or if two of them collapse to the same thing, right? Then my solution might be an entire line or entire plane, okay? Depending on how many independent equations I have in 3D. We could, of course, now actually generalize this, okay? These, what was that, 3D lines or 3D versions of lines are called hyperplanes in n-dimensional systems, so math has a name for them. Okay? But, so basically, at the intersection of n planes in n-dimensional system, okay, I will find one point. Yeah. It's much harder to visualize how those look like in anything beyond 3D, okay? But it does extend, and yes, we do come up with systems that solve for a lot of points. Okay? So then basically I have answered this long story. So if I had a system of 3 equations and 3 unknowns, the solution would be a point in 3D. That is at the intersection of 3 planes. That is if I actually have a solution, right? All right, well, move on to 3 and note that this happens to me like, this happened to me like 3rd time. I actually have a file that has this corrected. This is not a MATLAB class anymore. It's Python. In Python, I need NP and NP will now solve. So just proceed and let's keep solving for these problems. So first this number 3, and then flip over and start working through 4, 5, and 6. And I'm gonna go and correct that file because I actually uploaded the wrong file too. And so while you're working on it, this worksheet, by the way, will be your quiz for the day. So just please complete it.
Well, it's because of what your volume is going from. We have 2 districts. I used VRQ for my
So I printed the PDF even though my worksheet was okay.
That's different. I mean, it's the same art. Like 314 is like glass scales. Meters cubed.
That's oh.
So if you if you convert, it literally won't matter. Like when you say what is on board, the person has to go. It's literally just you're just taking that volume and you're multiplying it by 10 now. So the positive is 6. So it's literally being 10x.
The one oh, so you get that. How would you graph it?
Yeah.
Graph that. The intersections at 1, 2.
Yes, that's one. But I want you to graph this and this.
Put it at 2, 1 or 1, 2.
So this first one is 1.
That's 1 or 2.
If I put another one, x1 is minus 1.
I just want to know. I didn't know what you did.
Or plus 1.
Okay.
Then x2 is and then we do the same thing for the other one. And yes, they do intersect at 1. Check that. If you can actually draw a straight line, which I cannot. For me, it's
Yeah, not exactly.
3 halves.
Right?
it's gonna be
Oh, wait, no, I'm not.
Yeah, I'm not.
So this one will be like x equals to 1 plus 7.
So one of your equations is x equals minus 3 and 1 plus 7. It's just straight forward. Right.
No, I understand that. What are you thinking of wait, are you supposed to consider?
Yeah, I appreciate it.
Yeah, I don't know if you need
Yeah.
Did everybody get through number 4?
Yeah.
So do we see how the matrix is 3, 1, minus 3, 2? And then my vector of unknowns is x1, x2, and then 7 minus 4. So in number 4, if I look at this system, I'm looking for A, x is equal to B, or system that is. So what is my matrix A? It's 3, 1 in the first row, minus 3, 2. And my unknowns is a vector, column vector, x1, x2. Okay? And my right-hand side, B, is 7 minus 4. Yes? And if you don't see it, please multiply. 3, 1, minus 3, 2. Multiply that with x1, x2, and see what you get. Three times x1 plus x2. That has to be equal to 7. And then minus 3x1 plus 2x2 has to be equal to minus 4. Yes? So that is a way to generalize, because I can type in A and B into NumPy. Okay. NumPy, of course, doesn't care whether something is a column vector or not. We've been through that exercise. But I can actually then use solution X is NP linalg solve A, comma B. And I should also print it, of course. Now this is a 2x2 systems, and you were 2x2 system, and you were able to find that solution by hand. If it were larger, you wouldn't be. Okay? So let's just briefly test this larger thing. Okay? I could say my A how would I create a 100 by 100 matrix with random numbers? What do I type in? Like that, or something else? I don't want to print the matrix, but shape is 100 by 100. I can maybe print one of them. Okay. I have it filled with some numbers. Yes? Now let me give myself another B. Oh. Okay. And I can solve just the same. Now let's print X just for kicks. Whoa. Could you do this by hand? Okay. This is why we want to program. Okay? 100 by 100 system. You don't want to even type it in, let alone anything else. All right.
Could you scroll up to what you did for the symbol example?
This is the simple example. Okay, so 3, 1, minus 3, 2. This is my first row, second row. And then this B is a row vector, because Python only does row vectors. And then I can do np.linalg.solve AB and store the solution in X. So you can again do something much larger, and that's the whole point of programming. All right. Now this number 6. Woo. Has everybody gotten a chance to go through these? So in a diagonal system, it's kind of simple, because this is equivalent to which system? When I multiply my A with x1, x2, x3, what do I get? What's the first equation? x1 equals on the other side minus 1. My second equation is 3x2 is equal to 6. So my x2 is obviously 6 over 3. And then 5x3. So do you see that, how I get that by multiplying matrix A with the vector x1, x2, x3? So I'm looking for an equation, system of equations that is equivalent to AX is equal to B. And then 5x3 is minus 15, so x3 is minus 3. How about this system? What's the way to attack this one? The matrix is what we call upper triangular, because only an upper triangle above the diagonal is filled with numbers, the rest is not. So in upper triangular systems, I start on the bottom, because that's the easiest thing to attack. So my 4x3 is equal to 8, so that gives me x3 of 2. Then I plug that into the one above, okay? And that is 3x2 minus 2x3, so 3x2 minus 4 is equal to minus 1. Yes? So 3x2 is equal to 3. So x2 is 1.
Do we do this by hand or on the computer?
By hand, actually. You can do it on computer, but I want you to go by hand for a reason. You'll need to program this as an algorithm for any size. And then once I have x2 and x3, I can plug that into the top one and get x1. Everybody sees that? Everybody can try or at least attempt to visualize how they would program this back substitution? Given a system? Well, that's something we're going to do soon enough. But before that, so we want to basically think about how do we program these things. And there's an important thing to basically remember from these small exercises, because those things generalize to any system, we need as many unique equations as unknowns to actually have a unique equation. So just having a square matrix is not good enough. We also have some sort of need some sort of a guarantee that none of these equations or lines are parallel to each other, or planes. Okay? So my matrix A has to be so-called non-singular. Its rank has to be equal to n. That means that there's n independent rows in there. And these are basically visualizations of things that can go wrong. I will have numerical difficulty when things look like this. Okay? So I'm not quite parallel, but I'm nearly parallel. Finding solution in those cases is difficult. And before we actually proceed on creating an algorithm, we also have to write down things that we take for granted as we are actually solving by hand. The order of equations doesn't matter. You kind of eyeball things and you start attacking what you see is the easiest. Okay? That means that the order of equations and how you attack them doesn't matter. You can start with the last one, first one, third one, doesn't matter. Okay? That's important to know if you're creating an algorithm. You can always multiply an equation with a number. That doesn't change the equation. Okay? As long as that number is not 0, then you have just removed all of your information. Right? So I can multiply both sides by some scalar that is not 0. I can also add and subtract or make a linear combination of two existing equations and replace one of them by it. That's what we do when we actually do elimination, right? And we can actually go and program that as well. So these 3 rules are important in actually going and creating an algorithm. So I can always add, subtract 2 equations and replace an existing one without changing the solution. So we're going to start programming some, and then we're going to go back to doing things by hand before we program some more. Okay? So that's how we're going to proceed in this lecture. See you on Wednesday. So please sign your sheet and turn it to you. That's your quiz for today.